Good morning, everybody. Welcome to this nice lecture on the natural convection. I hope you still remember that in the last two lectures, we've been focusing on the calculation of H, the convection heat transfer coefficient. We talked about the convection coefficient on so-called external flow, flow over a flat plate, and we skipped the content on the for the other parts where we calculate the convection heat transfer coefficient, let's say over a pipe, around a sphere. Okay, these are fairly simple concepts if you understand the natural the flow over a flat plate. When we talk about the flow over a flat plate, over a plane, and we say the convection coefficient varies. Okay, varies along the flow. It's not a constant. Then I emphasize the differences between the local natural convection coefficient and the average convection coefficient. I showed you four different convection coefficients. Say for the laminar flow, for the turbulent flow, for the turbulent part, and the average for some part of a flow. Okay. Then we talk about the flow inside a pipe. For liquid, a pipe, we call it a tube, a pipe. Okay. For gas, we call the pipe a duct. Okay. These are the jargons or terminology we used in heat transfer. Then we say the convection coefficient H are different for turbulent flow, for laminar flow. Yeah. So, but basically, for flow inside the pipe, the convection coefficient you are given is all for the average of a pipe section. So we didn't show you the local transfer coefficient. Okay. Today, we come down to a different, slightly different phenomenon, which is natural convection. Let's see what it's about. I will first go through these objects first, but those contents marked, okay, those contents marked with a star, okay, are not, okay, are not required as an examination. Okay, these are not required. But overall, we need to understand the differences of a natural convection over, say, forced convection. And so the way to calculate the H convection coefficient is very different. Okay, so that will be the objective study. In particular, we analyze the natural convection inside enclosures such as double pane windows, okay, or sometimes called double glazing windows, because this is now widely used in buildings, and it is a very important component to reduce the energy used for heating and cooling in buildings. And so we'll spend some more time on this natural convection analysis. Yeah. So that will be the content of this lecture. Okay. Many examples that can help us to understand the differences between natural convection and forced convection. Now, I think some of you live in you have some international students. Some of you live in a very cold climate in the winter, right? In the winter, when the day is cold, you know what you do. You try to avoid high wind, right? You try to avoid staying too long in a windy condition, okay? Because you are experiencing a forced convection when there is a wind, right? So you feel much better when you stay in a place where the wind is weak, okay? So that is a demonstration of the differences between natural and mechanical and forced convection. In contrast, in Hong Kong, we have a very hot summer, and you probably would enjoy go to the beach, right? Then you feel if there is a wind, you feel much better because the wind helps to increase the heat transfer from your body to the surrounding. Yeah. So again, this is demonstration of the differences between the natural convection and forced convection. In general, when you have a forced convection, you tend to have a higher H, higher convection coefficient. When there is no wind, you tend to have a basically lower convection coefficient. Today we are looking at the cases when there is no wind, okay? There's no flow. So like right now you are sitting at your home, right? I think if you somehow open your window when there's a wind blowing towards you, you feel much colder, right? So in that sense, for practical purposes, you would prefer to have some wind. In one case, then you prefer not to have wind on the other case. Just now I mentioned about the differences between the hot summer and cold winter. Yeah. Today we focus on the case where there's no wind and how to assess the heat transfer coefficient. Yeah. But theoretically speaking, when we talk about forced convection, we mean there is an external force that generates air movement around the heat transfer around a surface. Therefore, the heat transfer coefficient between the fluid and surface is enhanced. On the other hand, if you put a cold subject in the calm environment, then the temperature differences between the hot surface and between the cold surfaces and surrounding fluid will generate a flow by itself. And that is what we call natural convection, okay? On the left-hand side of the slide, you will see a plate on which you place a hot egg, okay? And I don't know if you enjoy a boiled egg for your breakfast. I prefer scrambled eggs for my breakfast. Okay, I don't eat a boiled egg because you know why? Because it takes too long to cool it down, right? It's very hot. Okay, and on the right-hand side of this figure, you have a cold soda, a cold drink that may come out from your fridge. Okay, the temperature would be around, let's say, in a fridge, if your fridge is really cold, you can cool it down to 4 degrees Celsius. Yeah? The room temperature, let's say, depends on where you are, maybe 22 or something. In thermodynamics, you know what? When the air close to, say, to the can, say this air is cooled, its density will become higher. If we treat air as a perfect gas, the relationship between the pressure and temperature and density is described by this perfect gas law equation, right? So when the temperature say is lower, that means this on this side the equation has to be equal, right? That means the density will have to be higher. So what happened in the fluid when the density of something is heavier than the surrounding? It will tend to sink down, right? Okay, that's what you know. If you put something heavier than water, you know it will sink to the bottom, right? If you say push something that is light than the water, if you push it to the bottom of the water, it will float up, right, by itself. Yeah, and this is Archimedes Law. We know that an object that has a higher or lower density will tend to float upward or downward. So that is a physical mechanism of natural convection. Okay. Therefore, it is caused first by density difference. Yeah. But there is a second reason. Because the object tend to sink to the bottom because there is a gravity. Okay? Gravity of the Earth. You know, nowadays on TV we can watch a lot of phenomena. Sometimes you may have seen that an astronaut. You know what is astronaut? Is the is the human being flying in the outer space, right? Within a man-made satellite. Yeah, we have this human carrying satellite in the outer space where there's no gravity. Yeah. When there's no gravity, there will be no natural convection. Okay? If there's no gravity, even the air is cool, it just stays there. It doesn't move up and down. So, therefore, for natural convection to occur, there are two conditions. One is the fluid tend to expand or contract or shrink. So its density changes. Second, there should be a gravity. Okay, so these are the two fundamental things. And we use, for example, on Earth, we use G, okay, the acceleration, the gravity acceleration, to describe the gravity. Therefore, you can understand how the density varies with temperature, how large the gravity affects the natural convection heat transfer. Okay. Then let's assess how big this buoyancy force will be under say different density conditions. We use this ship, okay, the ship as example. A ship can carry a lot of cargoes. Why? That's because you have a buoyancy force to lift it up. How the buoyancy force is generated? Well, basically, for a ship, you will have a body below the ship, which is somehow separated into several apartments, okay? And that's for safety reasons. In case there is a leakage of water in one apartment, the other apartment will not be affected. Yeah, okay? That's why you try to separate your ship into several apartments. And these apartments are left more or less partially empty, so that you have a very low density here. It's almost inside is air. Yeah. So therefore, the overall density of the ship, that is say level with the water. This is the water level, okay? Yeah. So this is the part of the body that is sunk into the water. Yeah. Okay. This is submerged into water. Yeah. And so the buoyancy force is equal to this much, equal to the fluid, okay, surrounding fluid, that is water in this case. Yeah. Equal to this much. Yeah. Then the weight. How about the weight of the ship? The weight is the density of the ship body. Okay, that is average of the air trapped inside and the heavy metals outside altogether. Yeah. Okay. And the net force will be equal to this much. Yeah. Okay. Therefore, if the body density is much lower, let's say just it's hollow, it's just air, that's almost. Then this force is negative. That means it generates buoyancy force. That means you can put on extra say cargoes on the ship, yeah, and the ship will keep floating because okay, yeah. So the body immersed in a fluid will experience a weight loss in an amount equal to the weight of fluid it displaces, yeah. Okay. And so this is an example of the body force, and this is equation to calculate it. Yeah. Therefore, this is different. In reality, we use this buoyancy force for many practical purposes. In industry, in some heavy pollution industry, we'll build a very high chimney, tall chimney, and the smoke from a factory will be extracted by the chimney and released into the atmosphere. Yeah. So the pollutants will not affect, say, the ground level neighbors directly. Why? Because the hot combustion gas, right? Because its density is light than air, therefore you have a constant force acting onto it. Net buoyancy force that drives all the way up. Okay, drive it all the way up and into the upper atmosphere. So in that way, the chimney effect that can say help to extract the polluted air into atmosphere is due to the same mechanism, the buoyancy. Okay. In this page, let's see how can we estimate therefore say the density change due to temperature. Okay. Now we define a so-called volume expansion coefficient first. Well, and it is let's say the volume of a gas, right? This is in this picture here. Okay. We maintain its constant pressure here. Okay, constant pressure, and if you heat it up by adding some heat, right? It will expand. Yeah, that means imagine when the gas expands, it takes a bigger volume, but the total mass remains unchanged, right? So that means its density. By density, we mean the total mass in the unit volume actually becomes lower. Okay. So we define this coefficient expansion coefficient this way. Density changes with temperature, right? And divided by the original density itself, how much this coefficient is. And this is what we try to define, okay? In this sense, if you approximate this, say, derivative into a finite difference, delta p, delta rho, and delta t, you will find the density change. Density change is proportional to the temperature difference. Yeah, but here you have this is approximation. Yeah. By this equation, we mean this approximation because theoretically, this beta varies at different temperatures. Yeah. Okay. We know that the finite difference delta is approximation of the differential derivative. Okay. In that sense, the density difference will be proportional to temperature difference. Yeah. This is what we try to let you know. Okay. In other words, when a gas expands, okay, in a small volume, this change of the volume or the density will be equal to the this coefficient beta times the temperature difference. So temperature varies by 1 degree. You see. Then times the original density, that is how much it has been changed. Yeah. Now it can be proved for ideal gas, for a gas that obey this law. This is what I mentioned earlier. Ideal gas is a gas that obeys the perfect gas law. Should be this, for a perfect gas, you can derive this equation by yourself. Using this definition, please derive, okay? Beta for ideal gas is just the reciprocal, okay? The reciprocal of its absolute temperature. Here, the temperature must be used the absolute temperature, Kelvin, okay? So there's something you should remember. For example, for air that has a temperature of 27 degrees, for example, C, right? Its absolute temperature will be equal to, as you know, 273, right? Plus, okay. Plus 27. It should be 3. Therefore, it should be 300 Kelvin. Okay, Kelvin degree. Yeah. Therefore, for air, that is approximately at room temperature. This expansion coefficient is about beta for air at room temperature. Okay, it's temperature dependent, as you can see. A room temperature is about 1/300. Okay. Yeah, this gives an idea that we know how the air will expand when its temperature rises. Yeah, and we have this equation now. Its density change will be proportional to the temperature change by multiplying this beta coefficient. That coefficient is about 1/300 at ambient, say, room air temperature conditions. Okay, so that gives an idea why there is a natural convection. That has become the density difference. Now we also learned how we can estimate, okay? How can we calculate the density difference when the fluid is heated? Yeah. Okay, next thing is for us to understand how the airflow look like. And okay, near a hotted plate. Here in this picture, basically now what you have here on this side, okay, is a solid, and this side is air actually. By this slide, we try to show you even for natural convection, there is the possibility that the flow is laminar. Okay, the flow caused by the buoyancy force is laminar or turbulent. Yeah, turbulence means the fluid start to collide with each other, moves in say okay, in a drunkard way. Yeah, so that is the difference between natural laminar flow and turbulent flow, even in the okay, buoyancy-driven conditions. Yeah. Okay. At this point, I think I'd like to maybe during the break, I'll show you some visualized flow with natural convection. Yeah. Okay. Another thing is that this is the technique. This is called interferometer, and it's based on depending on the temperature difference. This meter can somehow visualize layers of different temperatures. Okay, when there's a temperature variation, it will kind of draw a line like this. Yeah, along basically the same line, the temperature is more or less constant. And in that sense, you also see when the lines are very close, it's a higher temperature gradient.
It's 10 hours.
Okay, higher temperature gradient means the temperature change is very large. Okay, if I draw a coordinate here, this is y from the surface, and this is let's say temperature. Yeah, you may have something like this. Yeah, so temperature changes very quickly from a high temperature at surface to the ambient temperature. Okay, then afterwards the temperature becomes fairly uniform along the y direction. We'll come back to this temperature change in another slides. Okay, so this is a different way to illustrate okay, how the temperature change. Notice this is x, y coordinates, right? Then we draw coordinate here. This is y, and this is okay. I draw another one. Temperature. Yeah, close to the surface, you have a higher temperature, and then okay, so a certain distance away, the temperature is the symbol is, maybe I wipe it out first. The symbol here is T infinitive. Okay, if I draw a coordinate in a different way, I draw a coordinate here. This is the y, and this is t. Okay, and this where okay illustrate how temperature varies from okay at this point. Excuse me. And okay, close to the surface, you have a higher temperature, and in the fluid, this is the ambient fluid temperature. We use the T infinitive, right? Remember, okay? And this slide illustrates how the temperature, how the velocity varies. Now, theoretically, you should have a higher velocity close to the surface, right? Because the Here the fluid density is the, let's say, lowest, because it's a warm surface. Yeah. So if I draw a density variation, maybe the density variation looks like this, I think. Okay. So the density of fluid is lowest close to the surface, and highest when it's at a certain distance away from the plate. Yeah. Okay. Therefore, there is more forces acting. The larger the density difference, then the larger the buoyancy force acting onto the fluid. Okay, you may say you have a larger force acting onto this one. Yeah. Okay, so if I draw another, the forces acting onto the fluid will be something like this. Yeah. Close to the surface, you have a larger buoyancy force. But because closer to the wall, the friction also very high. Therefore, the resulting velocity distribution looks like this. Yeah. Okay. The differences between natural convection and forced convection is that outside the boundary layer, okay, the velocity boundary layer, the velocity is also zero here. And because for a forced convection, we know it's different. For forced convection, if I use a different color, you have a say uniform velocity, right? For a forced convection, you would have a velocity outside the boundary layer when there is a wind. Yeah. Now, for natural convection, we don't have this velocity as indicated by the green color. Okay. So in this illustration, we are illustrating a warm surface. Yeah. In case of cold surfaces, you just put this figure upside down, and everything remains the same. Yeah. Okay. So you just turn these slides upside down. That will be the case with the cold surfaces. Okay. The next few slides, I'm going to very briefly introduce a concept rather than the actual solution. To try to let you know how actually we can find the natural convection coefficient. Okay. Let's we start from back, and then we go back. Yeah. Now our purpose is to be able to find this edge. Yeah. And how we can find it? Again, we start from the old way. Okay, I go back. How we can find the natural convection coefficient along all these cases? Remember, H is always found by this way. H times T surface and this is the heat flux, right? Equals minus K fluid. Yeah. And Okay. Sorry, this is not right. Not those parts. Y equal to 0 here, not the whole equation. No. In other words, the derivative is calculated at the very surface. Yeah. Okay. So this equation applies to both natural convection and forced convection. Yeah, it's all the same. Okay. Therefore, well, this equation is used by scientists or researchers to find the convection heat transfer coefficient. Okay? In other words, you got to find the temperature gradient near the surface to be able to work out what is the convection heat transfer coefficient. Yeah. Therefore, this is the scientific method to find. Okay. Yeah. If you remember, we have done some tutorial problems to understand this correlation. Yeah. Well, I have said this is a scientific method to find H, but we are engineers, so we will not spend too much time in doing this calculation. Yeah. The purpose of scientists is to find a method to calculate H, so that we don't need to repeat this calculation method in our design or in our say professional work. Yeah. Okay. So that's the difference between the scientists and engineers. Okay. Therefore, I go back to the few slides I skipped over. Now, this is the scientists. And therefore, scientists start from this fundamental flow equation, and by finding a solution for this equation, then he was able to calculate the temperature gradient. Yeah. But instead of doing the calculation, there is the one thing I wish you to understand. That is the Grashoff number. Yeah. Okay. And this is our original, the whole set of equation. Okay, for you to calculate the temperature gradient, how the temperature varies with velocity, with the position, how the velocity varies. So this is a 2D partial differential equation. And it's extremely difficult to find an analytical solution for this equation. Okay? And so those are the equations, and the following are the boundary conditions. Yeah. Okay. But while you are not required to know how to derive the equation, but you are supposed to derive this so-called Grashoff number. Okay, and this Grashoff number is for you to memorize and to understand what it means. Yeah. First of all, how this Grashoff number is defined? Well, we define all the dimensionless, so-called non-dimensionalized variables. Yeah. We divide the x by a dimension. Okay, for example, the height of the wall. Yeah. We divide all the velocity by a notional velocity. Okay, we don't know. We just say, let's say the light velocity is v. We don't know exactly how large that is. Okay. Then we define a dimension is temperature. You would find all the fundamental equations can be rewritten as this one. Yeah. And in this equation, you see all these are the variables, yeah, that need to be found. And this is the kind of coefficient of the equation. What does this mean? If you say one day you are able to find a solution for this equation, then you would understand in the solution, this coefficient will appear, right? As we know, if you find a solution for a differential equation, the coefficient in the original differential equation always appear in the final solution. Yeah, and the point that you may think is, oh, this is, it seems, only coefficient in addition to the Reynolds number. Yeah. But the point is, in case of natural convection, the Reynolds number is a dependent variable because the V depends on this term. Yeah. Therefore, this is the determining parameter for natural convection. Okay. Why? Then it's easier to understand this equation. Earlier I said gravity, that is the, on Earth, this will be 9.81, right? Gravity is the determining factor, right? Without gravity, there's no convection. Second, there is natural convection because the fluid density varies. Why? Then we define this expansion coefficient, right? So it's related to the expansion coefficient. Okay, even there is a expansion coefficient, why it expands? Because there is a temperature difference. Therefore, the temperature difference appears in the equation, right? The second, we can imagine that for natural convection to occur, it also depends on the scale, on the length of the pipe, of the surface. You can imagine larger the surface, then the stronger the convection, right? It's like the larger the ship, okay, then the total buoyancy force, the larger the total buoyancy force. Therefore, a large ship can carry more passengers than the smaller ship. Yeah. Now, eventually we understand it's the volume of the ship, it's not just the length of the ship. Yeah. Therefore, you have this cubic. Yeah, that means the volume, more or less, proportional to the volume of the plate. Yeah. Okay. So even the plate is only kind of L, yeah, in this way, but actually it's related to the total area of the plate plus the thickness of the boundary layer. Therefore, eventually, the natural convection depends on the volume, somehow, the volume of the layer of the air close to the surface. Okay? Therefore, we have this cubic there. On the other hand, we must know if the velocity has a high, okay, has a high viscosity, it will somehow hinder, okay, or reduce the flow. Therefore, the viscosity has a negative effect. Negative means it appears in the denominator, right? Okay, and this squared it means that it's somehow it's because of the equation, yeah. So it's a square here, yeah. Okay, so in this way, I hope you can remember the Grashoff number determines the natural convection. Okay, so that is instead of the Reynolds number, because then why we didn't explain the Reynolds number, because the V is not known. Okay, the maximum velocity is not known in natural convection beforehand. Therefore, this Reynolds number is actually independent, or it's the dependent variable. Okay. So this is the difference between natural convection and forced convection. We talk about this Grashoff number. Again, it's a German family name, German engineer, okay, who first coined this term, this dimensionless number. Yeah, okay. Okay, so now we understand the Grashoff number actually is also determines whether the flow will be laminar or turbulent in natural convection. Yeah. You can imagine when the warm fluid close to the surface start to move. As it's moving faster and faster, it will turn into laminar in the lower part, into turbulent in the upper part. Okay? So where this transition occurs, at the flow moving upwards, when the flow will turn into laminar or turbulent, well, for vertical plates, the critical Grashoff number is observed to be 10 to the power of 9. Okay? That's about 100 million. It's a big number. Okay, so 100 million. And so basically above this this position, the flow will be turbulent, and the start is laminar. But in natural convection, we don't have an equation to calculate the local edge. We only calculate the average for the whole plate, either only for the laminar part or for both the laminar and turbulent part. Okay. So scientifically speaking, the Grashoff number is a measure of the relative magnitude of the buoyancy force and opposing viscous force acting on the fluid. Okay? The second thing you should know is that in reality, sometimes you have the so-called mixed convection. Imagine you are standing outside. If there's no wind, your body is losing heat only by natural convection. Okay, but imagine there is say gentle breeze coming towards your body. Okay, then you will have a kind of mixed convection. If the wind is so strong and this buoyancy, the buoyancy force is so little in compared with the forced flow, then you have a forced convection. Yeah. Okay. When the Reynolds number, okay, when the Grashoff number is much smaller than the square of the Reynolds number, this will be the forced convection. You can use the equation you can use the equation we learned in the first lecture of natural convection. Okay, the week before last week. No, okay. Today we only focus on this case. In the case when the Reynolds number is small, Reynolds number is closer to 0. Okay. Right? So this is say graphic illustration. What is pure natural convection? What is mixed convection? What is forced convection? Yeah. So if you plate a hot egg on your plate for your breakfast, if your room window is closed, typically you don't have much air movement in the room, and you have a pure natural convection. Yeah. But if you are so eager to cool down your egg, okay, and you are in a rush, you can blow the cold air towards the hot egg. It cools down the egg quicker. In this case, it's a forced convection. Yeah, because the buoyancy force is so small in comparison. Okay, relatively small in comparison with the forced flow. Yeah, but somehow you have a weaker fan, smaller fan like this, and you do blow, you do generate a flow, but the buoyancy force still very say significant. Yeah, then you have this so-called mixed convection. In other words, the velocity is generated both by the fan but also by the buoyancy. Yeah. Okay. We have some equations, but we are not going to learn too much about it. This idea is good for you to have this concept, but we are not going to teach you all the equations. Yeah. Okay. And this is what we already learned before. Okay. And today we will focus on this one. Yeah. Okay. Okay. So let's have a short break, and we'll start at 10:30. Yeah. Okay. Okay. Hello, everybody. Let's resume our lecture. So eventually, we have this equation. We define the Nusselt number as we have defined before. Okay, and we can imagine that the Nusselt number will be a function of the, in this case, Grashoff number times the Prandtl number. Okay, Prandtl number, if you remember, is the A over the viscosity. Where A, okay, I write it. Prandtl number, just in case you forget it already. I write it down again. This is the Prandtl number. A, if you remember, is K conductivity over the rho times Cp. This is the thermal diffusion coefficient, A. Now, okay? This coefficient is we don't know yet. Yeah, okay? And And also the products of Grashoff number and Prandtl number, we call it Rayleigh number. Okay, it's Rayleigh number, RA. Yeah, it's very close to the RE, Reynolds number, but it's Rayleigh number. Yeah, Rayleigh, I think it's a British scientist. Okay, he somehow independently defined this number. I think first. Okay, it's the Grashoff number times Prandtl number. Yeah. So this coefficient C and N is what we need to find. Yeah. In general, the constant C and the exponential coefficient depends on the geometry of the surface and the flow regime. By flow regime, we mean whether the flow is turbulent or laminar. Yeah. And which is we use Rayleigh number to judge whether the flow is turbulent or Rayleigh number. Okay. And the N is typically 1/4 for laminar flow or 1/3 for turbulent flow. Yeah. Okay. Another important thing is that all the fluid properties are to be evaluated. That's the so-called fume temperature. It's average of the surface and surrounding fluid temperature. Okay, and then once you calculate H from this equation, we will be able to calculate the heat flow by the equation at the bottom. Yeah, okay. And both these two coefficients were found from experiments. That's okay, from experiments. Yeah, but are found experimentally. Okay, so that is where we got this natural convection coefficient. Okay. Finally, we have a table that from which we can find the convection coefficient we want. Okay, for a vertical plate like this, for example, this will be your cold window in a cold winter. For example, if your outdoor temperature is -20, that is extremely cold. Okay, your window surface may be 0 degree. Okay, I can share my experience when I once lived in a cold climate, so cold, right? And this is the wall. So when I woke up in the morning, I see frost formed at the corner window here. Okay, now the window surface so cold, the moisture in my room, okay, got frozen here at the corner of the window. Yeah. Anyway, if you want to calculate the heat, the convection coefficient at the wall surface, and this is the equation. That depends on this Rayleigh number first. Okay, calculate Rayleigh number, and depending on the Rayleigh number, you choose the equation. Or if you are lazy, you can always use this equation. Okay. Somehow, if I have a skylight window, skylight means if you live in a house, okay, and this is the roof of your building, you would build in some skylight windows. Yeah. So this is the inclined plate, and it's very simple. You just replace G, the gravity, by G times the cosine, okay, of this angle. And okay, that you get, then it's Then the rest will be same as this case. Oh. Okay, how about you have, say, I don't know, in some cold climate, you use a heated floor for heating. Okay, a heated floor. We call it floor heating. Okay. What you did, you bury some pipes under your wooden floor, in which you flow warm water. Yeah, this will make your room very cozy, very comfortable. Okay. Then we have this equation. You see, it depends on the Rayleigh number. Okay, find the Rayleigh. First, calculate Rayleigh number to see what are the values. Then use two different equations. Yeah. But if you are having a hot surface, okay, facing down, what does this mean? Say this is your room. You put a hot surface at the ceiling, right? And well, basically now the heat transfer, the convection from the warm air down to the room will be less efficient because the warm air does not move, does not coming down, it just sticks here. Okay, so it's less effective for heating. You can see actually even you have a great Reynolds number, Rayleigh number here. You see the okay. The Nusselt number here, you see this coefficient is 1/4. Yeah, but for this case, the coefficient is 1/3. Yeah, okay. So that means even with a very high Rayleigh number, the edge will be much lower. Yeah. Therefore, say the direction of the temperature gradient matters in natural convection. Yeah. Okay. In forced convection, if you have air blowing towards the plate, you have the same correlation in forced convection. But in natural convection, a hot surface facing upward or facing downward makes difference. Okay, this is very important. There are some other geometries which are very similar. If you have a vertical cylinder, this is like a human body, right? You have this natural convection. Basically, if the diameter is relatively large in comparison with the height, the whole cylindrical surface will be treated as a vertical plate. Yeah. In other words, you rotate, you expand the surface area as a plate. Okay. That should be 2 pi r. Okay, that is the width and times the height. Yeah. So when the d is large enough, it's the same equation as for the vertical plate. Yeah. For a horizontal cylinder, that means the air flows this way. Okay. I mean the buoyancy force acts in this direction, and then you have this equation. Yeah. And you the diameter of the pipe. Okay. For the characteristic length. Yeah. And for a sphere, you have this equation. Yeah. Okay. How about the just now? What we are talking about is the case when the temperature is a constant. How about the case when the temperature, the heat flux is constant? For example, you may have an electrically heated plate, as I said many times before. In that case, we still use the same. We still use the same equation as approximation. Okay, but the only difference we need to assess the surface temperature in a proper manner. Yeah, and but the point is, you don't know the surface temperature beforehand. Yeah, so you need to do it in a so-called iterative manner. Okay. Okay, this is what I mentioned to you already. This part. In general, a hot plate, okay, facing upward, if a hot plate facing downward, in simple words, okay, this written is a bit awkward. Yeah. Hot plate facing downward, okay, this case, the convection a bit weaker. Yeah. A hot plate facing upward, this one. So heat transfer is a bit stronger. So this is the case. Yeah. In the case of a cold plate, this is the other way around. Okay. So this is that this picture is about. Okay. And so we come back. This table, that means this is the hot plate facing upward, right? This is the hot plate facing downward. Yeah. For a cold plate, it's the other way around. A cold plate facing downward is better than a cold plate facing upward. Okay? And this is the illustration why. Okay. Now this depends. Even if a fuel, say a plate, it's heated, suspended in the air, if it's facing upward, yeah, the natural convection is. The air tends to go upward by itself, right? But if it's the hot plate facing downward, imagine the air is heated here. Okay, maybe I change into a warm color. The air was heated up. So this air is lighter, right? It tends to float, buoyancy force acting this way. And then what's happened? This is the wall. This is the surface. So you see the warm air tend not to move because of the surface action, right? Imagine this is a hot balloon. I think I illustrated this before. The balloon will stick to the ceiling, right? I don't know if you have experience with a helium balloon, a balloon that has a light in air. If you let it go, it just fly up. In a room, it will stick to the ceiling, so it moves no more, right? But on the other hand, if this balloon is heated, then it goes upward, right? Okay. Then when it goes upward, then some cold air comes in. So you have a constant balloon going up, and then cold air come in to replace it, warmed up again, then going upward again. Therefore, for this reason, the hot surface facing upward will have a continuous stronger airflow than when it faces down. Okay? So for this reason, sometimes it's a very important question for our profession. So we have a room, right? In a cold climate, you have a very cold window surface, right? You want to keep your window warm. It's better to heat your room from the floor. It's less effective to heat your room from the ceiling. Okay? So that's the application. In cold climate, it's very common to have a radiator located below the window. So the warm air will counteract on the cold air coming down. So it's heated up your room more effectively. Okay? Now I spend some time to explain the horizontal cylinders and spheres. Natural convection around the cylinder. Okay, this is a cylinder, right? So the flow around the hot cylinder will like this. Yeah. In fact, you would have a different heat transfer coefficient. You have a higher heat transfer coefficient here. Okay. And lower here because the temperature gradient. This is topic I think I will skip over. Okay, this is about the fins. We talked about the fins before, right? And I will not talk too much about it. A fin, for example, you may have a plate like this, right? And now we add by fins, we add some, say, for example, we draw it a bit longer. We add a number of extended vertical surface to the original flat. Okay, these are called fins. The purpose of use fins is to increase the heat transfer, the contact surface between the solid and the air. Okay, so that you have more convection heat transfer. The topic here is about how to determine the distances between the fin to make the heat transfer more effective. Okay, this is more kind of engineering design. You will learn this when you need in your profession. We don't have much time to about this topic. Yeah, so okay. So in the next half an hour, I will spend some more time to explain the natural convection inside enclosures. What do we mean by this? Because in our profession as building service engineers, we need to increase, say, the heat, to stop the heat transfer between the wall and the outside. In cold climate, that will keep your room warm, right? In hot climate, it helps to reduce, say, the solar heat getting into our room. Yeah, okay. One other technique is so-called double glazing. As we talked to before, instead of using one layer of window, you have a double layer of glasses. Yeah. Then there will be a so-called cavity inside a very thin layer of glasses. Yeah. Okay. For example, inside you are keeping your house warm. Outside temperature is low. You still have some heat loss. Yeah. Okay. And theoretically, you'll have this heat transfer coefficient from this surface to the air, then air to this side. Yeah. Okay. Now later we will see, we instead of using this two convection coefficient, we just calculate the overall heat transfer coefficient. Yeah. So that is the overall heat transfer coefficient is reciprocal is the overall resistance, right? Okay. Actually, as we know, the total resistance is H1 plus H2 1. This is the total resistance through a double layer, say through this air layer. Yeah. First you have this convection from here to here, that's one resistance. Then from the air to this side, you have another resistance. Yeah. The total resistance is the is this two. Now we'll see that for the convenience of convection heat transfer calculation, instead of calculating the two edge, which are basically equal to each other, actually, yeah, we just calculate the overall resistance, yeah, overall edge, which happen to be equal to the individual by this equation. Okay, so only calculates overall edge. Yeah. Okay, so that is the something special about natural convection in the enclosed enclosure or thin layer of the convection. Yeah. Okay. One thing. The other thing I wish to share that when we use this, instead of using the, that's interesting. Okay. Instead of using the height HLH as the characteristic length, we use the horizontal thickness. We use the thickness as the characteristic length here. Okay, or the distance. And the temperature difference now is also different. It's the temperature difference of the two surfaces here. Okay, T1, T2 for the Rayleigh number calculation. Now within this layer, the flow can also be turbulent or laminar. Now we use this criterion to judge if the flow is laminar or turbulent. Okay? So this is one thing. But if this layer is put in a horizontal manner, you got to be very careful. Okay? Hot plate at the top. In other words, if for example, you have a sky window and outside it's hot in the summer, and then in that case, there will be no fluid motion within the layer. Therefore, what's happening inside is a pure, okay, conduction heat transfer in this case. Okay, then you can use the conduction heat transfer equation, and this Nusselt number will happen to 1. Yeah, Nusselt number equal to 1 means you look at show your equation. That means H, okay, L K equal to 1. That means H equal to K over L. And this is the conduction calculation, if you remember, right? Okay. For calculating the conduction heat transfer from this side to this side, this is the equation we used to use. No. On the other hand, if you have a hot plate at bottom, okay, you can imagine this way: the cold warm air from the hot surface will tend to move upward, right? Then the cold air, if I use different color, the cold air at the upper will move down, right? So you will have this kind of constant airflow, circulation of the air, yeah? And periodically you have this kind of movement of the air, okay? And so here the air goes up, yeah, and here the air goes down, yeah, okay. And so that in that case you have a strong convection, yeah. Therefore, when you calculate natural convection, sometimes you got to ask yourself: is there a airflow in this case, or is it pure conduction? Okay, you got to ask this question first before you decide how to calculate in the next step. Okay. Therefore, for the calculation of the overall heat flow through this layer, it changed into case, right? We calculate the heat transfer by using an edge, right? Then from the definition of Nusselt number, because Nusselt number defined this way.
It's 11 hours.
It's H L over K. Therefore, H will be equal to K times Nusselt number. So H right, divided by the K, by the L, yeah. So you substitute this H with this equation, you get this equation, yeah. And if you define this part, okay, this K times Nusselt number as effective thermal conductivity. Yeah, and then looks like you are calculating the heat transfer in this layer as a pure conduction problem. And the only difference is that this original K of pure conduction is replaced by effective conductivity. Okay, and this will be able for you to cover the pure conduction. If Nusselt number is equal to 1, then it's a pure conduction, right? Okay. Next, let's see what are the equations for you to calculate Nusselt number, right? We don't know yet, okay? So here are the equations for you to calculate Nusselt number for flow over a flat plate, yeah, over this layer. Okay. Now remember, this L is used for the Rayleigh number. Okay. Remember one thing though: if the hot plate is at the top, hot plate at the top, Nusselt number simply equal to 1. Okay. This is something you got to know. Yeah. Okay. The reason of having two equations is because of the turbulent and laminar. Yeah. Therefore, you got to calculate your Rayleigh number first, to determine whether it's the laminar or turbulent. Another equation that this is for typically for gases when the Prandtl number is within this range. For water, silicon oil, and mercury, the Prandtl number is basically much greater. Okay, Prandtl number is much greater. It's much greater than 2. It's typically 10 or so. You got to use a different set of equation. This different set. Okay. Basically, now this equation, this horizontal for the horizontal rectangular closure. This is the equation. Okay. How about the vertical then? We have the vertical, right? This is more like our window. Okay, window pane. Basically, now we are talking about a case when, in general, we are talking about a case when the this case, H and L over L is much smaller, much larger. Yeah. In other words, this L is much smaller than H. Yeah. So it's a thin layer of large surface. Okay. Again, we have these different sets of equation. Now, it's primarily because of the different Rayleigh number. But also this dimension matters. Okay. Dimension. This is more or less for a kind of let's say not so thin layer, for a thick layer. It's more like a geometry. It's more like this kind of geometry. Yeah. Okay. H and L are about the same size. Yeah. For a very thin layer, you have this set of equation. Okay. And you can see this is these are the different equations. So Rayleigh number, but also this relative dimension between the thickness and the height. Okay. Another case is that you may have two layers of pipe. You have internal pipe, you have external pipe, and in between you have another fluid. And this is used for some heat exchangers. Okay, in our refrigeration system, you may have such a design. In this case, we also define a K effective. Okay. Remember the conduction equation between the two layers of of cylindrical system. The Q will be equal to K over a log. Okay, the out diameter over a D, and divided by 2 pi. Okay, this is the equation for us to calculate pure conduction. Okay, now we are using the same equation, but we use the effective K. So here we don't use the constant Nusselt number. Okay, we just use the effective K over the pure conduction K. And now this is the equation. On the right hand side is the equation for to calculate the effective conductivity. Again, Prandtl number, but Rayleigh number. But in addition, we have this this factor. Okay, this is purely dependent on the geometry. Yeah, this is called geometric factor for concentric cylinders. Okay. When this number is smaller than 1,100, it's almost pure conduction. Okay, and therefore, when this number is large, you need to do this calculation. If it's smaller than 100, you can just use pure conduction. Okay, this is of course two concentric horizontal isothermal cylinders. Yeah, this is a horizontal case. Okay, because in natural convection, the orientation matters. Okay, the direction relative to the gravity matters. Therefore, whether the pipe is horizontal, vertical, or inclined matters a lot. Yeah. Okay. One thing we should be aware, when you have this two layers of, say, glass, right? Beside the convection heat, say, due to airflow, the two sides will be exchanged heat by radiation directly. Okay? So you always have a kind of combined transfer coefficient. Yeah. And when you have these two planes parallel to each other, basically this is the equation for you to calculate radiation heat transfer. Yeah. And if you define a so-called effective, okay, this is what we call, we have not talked too much about this, the so-called emissivity, right? This is the emissivity, yeah. And of the surface, then this emissivity could be replaced by the average emissivity of the two. Okay, so that is the equation for the radiation part. Yeah. Okay. And earlier I mentioned about combined natural force convection for this case, when neither is negligible. Yeah. And so far we have learned the force convection. When the velocity is high, you can ignore the natural convection effect, and or the other way around. But in some cases, you have to consider both, and that is the something I'll go to learn after in the future. Yeah, there are equations available. Okay, for example, you can estimate the two, then you modify, you calculate the combined effect. Yeah. Okay. For example, we have pure force convection coefficient, indicated by the two different lines. Yeah. And we have the approximate solution. Yeah. And depending on the geometry, you can sometimes you need to estimate this combination of the number to see if you need to make certain adjust of the self number you calculated. Okay. There are some on the other hand, for engineering design, one thing you should be aware that in some cases the force convection may somehow counteract with the natural convection. For example, this is a warm hot plate heating up the air. If you blow the air this way, it will enhance the overall heat transfer coefficient. On the other hand, if the air is flowing downwards, but somehow you generate a flow from this side, you can imagine the flow will be changed probably like something like this. You're blowing this air. Yeah. Therefore, in some region, there will be no flow because the flow leave this way, the flow leave this way. So you may generate some stagnant point where the heat transfer will be very slow. Yeah. So this is what we try to illustrate in these slides. Yeah. In this case, if you do encounter such a practice in your engineering design, you got to talk to your senior management, senior manager, senior engineer, and may consult on some heat transfer specialist. Yeah, if you are a design engineer program, okay? This equation, as I said, you don't need to bother. Yeah, I only wish you to have a concept rather than to know exactly how to calculate the mixed convection cases. Because I can tell you the current equation available in the handbook, in the textbook, are not so reliable. They were obtained some long time ago by experiments, and the results are very limited to a very simplified conditions. Okay. With a modern, say, computational method with computer, we can now calculate the heat transfer case by case with a better accuracy, and that is called numerical heat transfer calculation. Because this is an introductory course, you don't learn so much in computational heat transfer. Although I introduced you the numerical methods, remember, right, in the conduction part, and that is a very powerful tool. But in introductory heat transfer courses, we didn't learn so much about the tool. Such a tool, we just give you an idea or concept. Okay. This is a more advanced topic. Again, I tend to skip this part. Yeah, not talk too much about it. Okay, and so I skip some contents. Partially because of the noise from my neighbor, which I cannot stop because they have a legal, they have a legitimate thing to do. Okay. Do remember the major concept, what we have today, what is the mechanism of natural convection and how different it is from the, from forced convection. Yeah. Instead of using the, say, Reynolds number, now we have this Grashoff number, and further we have the Raleigh number, right? Okay. And remember, Raleigh number defined as the Grashoff number times the Prandtl number. Yeah. Okay. And then we use this Raleigh number to judge whether the flow is laminar or turbulent, right? And based on laminar turbulent, we have equation to calculate the Nusselt number, or the so-called effective conductivity for an enclosure. Yeah, and in that way we are able to handle the natural convection problem. Okay, so those are the basic idea I wish you to have, and also to understand when the natural convection does not occur. Okay, so that these are the major concept. Yeah. Okay. Let's have a short break for about 10 minutes. Then we'll continue with the tutorial problems. Okay? Hello, everybody. Let's start our tutorial sessions. But before we look at the tutorial problem, I just wish to share with you something from the website.
A way of saying, be patient, things take time. So watch the pod all you want, pull up a chair, make a day of it. It could be very educational for someone like you. If you don't watch it, here's what you'll miss. First, steam will form between the water and the lid. Next, small bubbles will appear around the bottom and edges of the pot. Finally, the bubbles will become large enough to break the surface of the water. Step 5. Once large bubbles are flowing in steady streams from the bottom to the top of the pot, the water is boiling. That's it. You've done it. Cue the trumpets and congratulate yourself. You're at least as smart as a not-so-smart monkey.
Well, that's just something about where is my? Oops, what am I doing? Okay. Yeah. Okay. Well, I think you all have seen some boiling water, right? I just, using that video, I try to give you an idea about the so-called natural convection. Yeah. Okay, boiling water is a natural convection because the pan, the hot pan surface is very hot, so water start to circulate, and especially when you have water bubbles, and when the water bubble start to move, so you can actually see how the water moves. Yeah. Okay. So even without boiling, what I'm trying to, even without boiling, the water is moving around, which you just don't see it. Okay. Now this is a tricky problem. The point is, if I draw on one side is hot water, boiling water, 100 degrees. On the other side, it's a cold water. I don't know if you love the Chinese hot pot. You have this so-called I don't know. Do you have this kind of pan? On one side, you may have a spicy sauce. Spicy, okay. On the other hand, you have some normal, ordinary, yeah. But anyway, here we have this hot separate plate. They have plate separate the two sides in the hot pan, yeah. Well, this pan has a thickness of, I don't know, 25 millimeter thick with a K. 15 watts. Okay, meter Kelvin. The heat transfer basically looks like this. This is 100 in the hot water, and then comes down to here, and the temperature changes into 70, right? Okay, so that is the I don't know what this line come from. Oops, all gone. Okay, I draw it again. The temperature. Okay, this is how the temperature changes from one side to the other. If I draw this coordinate, okay, x, I draw coordinate, say, this is temperature, yeah. This is how the temperature changes as a function of x, right? If I tell you in our earlier study, we typically tell you the convection heat transfer on this side, on H1, on the H on the other side. Yeah, H1, H2. And then the total Q, heat flow, can be easily calculated. Remember, T hot minus this plus over 3 resistances, remember, right? The 3 resistance, if we draw a circuit here, okay, can you write the 3 resistances? This one is H1 over H1, and this side is H2 over H1 over H2, right? And this resistance is the thickness, okay? And then the thickness of the plate over K, conductivity. Right? Okay? And, well, if you know H, you can solve the problem very easily, right? Okay? Once you find the Q, then you can find the temperature on each side. It will be equal to T hot minus T1 over say R1, or equal to T2 minus T cold water over R3. Okay, maybe I write it again. This is R1, and this is R3. R3 is basically okay. These are 2 equal to each other, right? Okay. Well, once you know H and you know the convection heat transfer, this is the way to give an answer to the problem. Okay, determine the temperature of the plate. But now nobody tells you what are the H1 or H2. You are supposed to find out H1 and H2 by yourself using the natural convection coefficient we have learned in this subject. One thing. Yeah. Okay. So that is what the solution is about. Second, Well, the solution simplify the case. Yeah, the solution given a simplified case, assuming this side, assuming, okay, assumption. This is not necessarily correct, but let's say assumption T1 equal to 100. Okay. So in other words, the T1 is already known in this equation. Now here, it's assumed to be equal to here. So it's the distribution. We are use a different color. In the solution giving, it assume that the temperature is something like this. Yeah. So the surface temperature here is equal to the hot water temperature. That is not a necessarily correct assumption. Okay. If I have to tell you, although this is solution given from the textbook, I have to tell you in your examination, if you make this assumption, I think I would say it's wrong. No. Unless the question tells you that this is the surface temperature on this side is equal to this one. Yeah? Okay. So this is a questionable assumption. Yeah. Okay, that's one thing. Anyway, so let's look at solution. The solution is assuming this side the temperature is already known, and it's assumed to be 100. And it is not necessarily a good approximation. Yeah. Okay. Therefore, the solution looks complicated. You first have to assess have to guess the temperature. Okay, by assuming the surface temperature on the cold water side as this. Yeah, this is assuming is okay because you are going to correct this. Yeah, you assume it here, but you will change it afterwards. Yeah, so this is the procedure. This procedure is okay. Yeah. The procedure is that this side is given as 100, and that is a problematic assumption in reality. Okay. Now, the problem is that to find the edge on this side, you must know this temperature first, but we don't know. Okay. Therefore, this is we started this so-called iteration procedure. Okay. Iteration. Or so-called try and error procedure. Yeah, okay. It's like ask you how deep the swimming pool is. And, well, you don't know, but you have several, say, ruler. You just, but you don't know how deep. So you take the first ruler, you cannot reach the bottom. Okay, then you change another one, and until you find one. Okay, this ruler reached the bottom, so that is the depth of the water. Yeah. So this is the case. You don't know the temperature, but only after you know edge, you can calculate the temperature. But the point to calculate the edge in natural convection, you need to know T first. See, that become a kind of dead loop, right? Therefore, you have to assume one and calculate the other. Then after you calculate the edge, you can recalculate this T. And then if the T is equal to what you guess in the beginning, that's it. If not, you continue this try and error, you will find one. Okay? So assuming that this is 53.5, you start to calculate the Rayleigh number by assuming this number, okay? This is assumed. This 53 is not true. Anyway, you get the Rayleigh number. Now you can calculate Nusselt number. After calculating Nusselt number, you get H, right? Okay? Then after you know H, you can calculate this temperature again. This is called first iteration. Well, it's not 53, it's 43. So what I get, then that means your guess is not right. So what I need to do next? Next, using 43 again to calculate the Rayleigh number and then to calculate the Watt number. After several try, you will find, okay? For example, after the 5th and 6th try, the surface temperature is almost not changed. Then you can take this. This will be your answer. Okay? So that is, you see the trouble. Yeah? Okay, so finally I come back to the initial problem. I think in this question you're going to assume one temperature first, but also to assume this temperature is not known. Yeah. Then you calculate, you do this calculation by iteration. Then you can find the right temperature on both sides in a similar procedure. Okay, that is the real true, say the more realistic answer to this question. Okay. This is another numerical example, which is a bit different. It's a uniform heat flux. For example, you have a solar collector. You have the solar radiation comes on. That will give you a solar uniform heat flux about, let's say, 800 watt per square meter. If you are enjoying a sunbathing, and that will be the heat flux onto your body surface from the sun, okay? Now here is, instead of this is a plate, maybe a solar collector, a PV panel, photovoltaic panel, okay? And on the other side is cold air and surrounding of 5 degrees. It's assumed that the mid temperature is 2055 here. The question asks you the heat flux from this side. I would call this a EU imposed question. Okay. Basically, to do this calculation, you don't need to say whether this uniform heat flux or not, because this temperature already given. So you don't need to bother on the other side. Okay. You don't need to bother on the other side. Yeah. So all you know, okay, I know this is you have a uniform heat flux. Now I know this temperature. I'm going to calculate what's the heat flux. Okay. Let's see how you can do it. First, because you know this surface temperature, you should first find what's the conductivity of the air and Prandtl number, also the expansion coefficient, so that you calculate your Rayleigh number first, okay? I don't know, the Rayleigh number is missing, okay, the data is missing, but it's here. That's the Rayleigh number you calculated. Yeah. Once you get this Rayleigh number for a hot plate, you can refer to the table and to find the equation to calculate Reynolds number, or Nusselt number, which is this one, right? Okay, then you calculate the heat transfer coefficient H by times K divided by L and times Nusselt number you got. This is the Nusselt number you calculated, so you get H, right? Okay. Then total heat flux is equal to the convection, natural convection, plus the thermal radiation, okay? Which we will learn more later about, yeah. So that's about 500 watts per square meter, yeah, okay? The next question is a bit different. You look at the question first. This is basically a window. Okay, wall. Okay. I hope you have read the question. Is it clear? Again, now the question is still given that this internal surface temperature already given. Okay. In reality, in your real life, we typically only know the outdoor temperature, right? We know the indoor temperature we want to be comfortable, but we don't know exactly what's the surface temperature. Yeah. But anyway, in this question, this internal surface temperature is given already. Yeah, based on experience or whatever. It's asked you to calculate the convection heat transfer coefficient on the inner surface of the window and the rate of total heat transfer through the window. Yeah. And see the combined natural convection and radiation heat transfer coefficient on the outer surface of the window. Well, it's also asked you, is it reasonable to neglect thermal resistance of the glass in this case? Okay. And let's see step by step what the solution is. Okay. First, before we go to solution, the convection transfer coefficient on the inner surface of the window is that we assume this is a natural convection because the cold air close to the window will come down. Yeah. So we treat the window as a vertical plate, and there is a natural convection, and we will find out this first. Yeah. Okay. Let's see. You need to find out these parameters: conductivity of the air, the viscosity of the air, the Prandtl number of the air. Okay. And you always need to know how to read a property table. Yeah. Okay. And this is calculate the expansion coefficient of the air. Okay. Next. The Rayleigh number. Yeah, this is the Grashoff number times the Prandtl number. Okay. And then this is the equation. You always use this equation to calculate H, which is equal to 3.9. This will give you an idea, in fact. Normally, the natural convection coefficient through the window is just about this large, 3.9 or 4. Yeah. Remember, in Hong Kong, we run air conditioner in the summer, right? Air conditioning will generate some airflow, so it's not pure natural convection. We may have a higher convection coefficient. Yeah. Okay. So that's one thing you should know. Anyway, so once you know this natural convection, you can also calculate the radiation from, this is the window, right? And then you have the room. Okay. Room is 25. The heat transfer partially by convection, partially by radiation from the room to the surface. Okay. And this is the equation for us to calculate to approximate the radiation from the room surface to the window. So, well, here give you this figure give you an idea that actually you see radiation transfer is a bigger portion than convection heat transfer from the room to the window surface. Okay. This is the case in cold climate. Yeah. And then you can calculate the total. You can determine the outside surface of the window by using the conduction equation here. Okay. This is the conduction through the window glass. Because we know the interior surface, which is 5, and now we want to find what's the external surface temperature, and we use the conduction equation for the window, yeah, and which happened to be 3.65, okay, and if you treat the outside convection and radiation as convection, yeah. So what's the so-called equivalent combined coefficient, heat transfer coefficient? Well, this is the equation for the convection part from outside surface to the outside air. Yeah, this outside surface of the window, this outside air. Then you can see that's combined, and that's pretty high. See, it's 20. Yeah. Okay. For the third question last question is to ask you to determine if we assume the outside surface is 5, how much the heat loss is, and well it's a small resistance. It's only about 4.5% error. Yeah. Okay. Because the glass resistance is only this much, and the total should be 25. This is not. I'm not sure this is the right way to assess the error. If you include the glass or not. If you ignore the resistance of the glass, what should be the error of calculation? No. Okay. And okay, so that is the idea. Yeah, the idea is that if you assume the two sides at the same temperature, in other words, you assume this glass has a 5 degree here. Yeah, so you don't need to the outside also 5. Yeah, what will be the difference of the calculation? Okay, in fact, you will see it's not much difference probably. Okay. In this question, we are talking about a single pane glass, okay, against a double pane glass. Now this, I'm not sure, this single pane or double pane is not, sometimes we think that more common is called single glazing, okay? Or double glazing. Because a single pane or double pane would be interpreted as you have a single glass, another piece of glass, and the two pieces can be open or closed separately. That would be a double pane. I don't know, that's my understanding of my English, okay? Well, the double glazing is more common. It's about double layer glass, yeah, double layer window. Therefore, you use a single layer or double layer rather than a single pane or double pane, okay? To avoid any confusion to people. Anyway, let's see. You have a single, let's see the differences of a window in this case. Yeah. And now the airspace is 64 millimeter here. Okay. Yeah, you how thick that is. Right here is my phone. Okay, it's just maybe the thickness is made just like this foam. Yeah, between the air layer. Okay, so it's a very thin layer of air. Yeah. Okay, that's about 6.4 millimeter. This is the old foam actually, but it's very thin. This one. Okay. It's not so cold. Outside only 7.1. Inside is 22. Yeah. Of course, in the winter, if you maintain this temperature, this 22, you got to use heat inside the room, right? And the question is, once you use say double layer glass, you would need less heat. Yeah. So now the question asks you about a house with 70 square meter of windows. How different of the electricity bill if you use a double glazed window or single glazed window? Okay, that's the question. Okay, so let's see how the comparison. Okay. I think the question already this is what we found from the table. The U, what is the U factor? U factor is overrule. Okay. U overall equal to the total thermal resistance of the from indoor to outdoor. Okay. What's the thermal resistance? It's H indoor. It's H1 over R1, right? The outside is the H1 1 over outside. Plus the total resistance of the window itself. Yeah. Okay, that's the window. Anyway, so I think here's what the figure is given, and but whether you include H1 and H out, okay, inside outside is another question. Yeah. Okay, let's see how the question look like. Here it says the two single layer window and double layer window only makes this this much difference. 18 minus okay, indoor-outdoor temperature difference, and that's okay. Now what you can see, how about if the outdoor temperature is minus 17? In an extremely cold climate. Yeah. Obviously you can see the colder the outside, the greater the difference. Yeah, if it is minus, okay. Now here there is a positive 7 outside. Yeah. So and the difference is that much. Yeah. And it only save you 27. This is US American dollars a month. Yeah. Okay. But if it's very cold, the difference will be larger. You can do a comparison yourself here. Okay. So that makes a lot of difference if the climate is cold. Yeah. Okay. I think that's all I have prepared for this lecture today, for this natural convection. And but the last question here is not really about natural convection. It's already about when window design. Yeah, in this case, and it didn't ask us to calculate the reduced, say, edge inside the window pane. Okay. In reality, we want to estimate the real, say, effective K for the double glass, the window, to be able to do this calculation. But somehow in this question, all these calculations required are, say, ignored. Yeah. Okay. So with that, I think I quickly finish my lecture and tutorial today. So we'll leave you more time for you to ask me any questions you may have. Yeah. I have to tell you, I haven't got time to mark your scripts yet. Again, I'm hoping that I can give you the scripts of your, the mark of your scripts and last tests, and by next week. Yeah. Also, after next week, 2 weeks later, we have another test, which will cover all the contents until next week. Next week, we'll talk about the heat changers. Yeah? Okay? So, in other words, in the next text, we'll cover convection heat transfer and heat changer design calculation. Yeah? Okay? See if you have any questions you may have, you may type in the chat window or you may raise your hand. I will let you speak, okay? Any questions? Okay, if you no more questions, then you have more time for lunch and enjoy your next lecture. Okay, see you next week. Bye-bye.